So it's about if we have a current in a uniform B field which is perpendicular to it. So there will be a force acting on this wire with current. So depending on the direction of the current, then there will be the force. Okay, suppose that for part B, maybe first for part A, if there are no current, then there will be no force acting on the wire. And if there is a current going from the bottom to top, and B field is out of the page. So I cross B, I pointing to the top, and then the B pointing out of the page. So the force will be point to the right side. And for this case, I is going from the top to bottom. So the force will be point to the left side. So here let's consider a sample problem. Okay, so here a strict horizontal length of copper wire has a current I equals 28. Uh, and there are some gravitational force acting on it, and we can see that yeah, the magnitude of and the direction of the minimum magnetic field to suspend the wire, which means to balance the gravitational force acting on it. So the linear density of the wire is 46.6 gram per meter. So we can calculate the mass of this wire. So as we know, the gravitational force is mg pointing to downward, and the current is pointing out of the page, and then the B field pointing to the left, to the right side. So the force acting on the wire due to the Lorentz force will be pointing to the upward. So we want to make FB the magnitude of FB equals mg. And so we can write so ILB is the force, is the Lorentz force for a current wire. So which is equal to mg. So B will be mg over IL. So we know that actually we don't really need to know about the length, because actually the length will be cancelled with itself. So this is the density. This is the density. So m over L is actually 46.6 gram per meter. So we need to change it to kilogram per meter as the SI unit. So it is times 10 to minus third power, and then G is 9.8, I is 28. So the B would be 1.6 times 10 to minus 2t. So this one is pretty easy. So the next we talk about the torque on a current loop. So as long as we have a single wire, there will be a force acting on it. So here, suppose we have a loop. Suppose we have a loop. Suppose consider you go to barbecue, or you have some meat in this coin and then try to rotate. Yeah, it will be quite nice, maybe. So so consider there are some current. There are some current going in this loop, and there are a uniform B field generated by two large magnetic bar. So this is the north pole, this is the south pole. So the magnetic field line between these two magnetic bar will be approximately uniform between this area. So so we can consider there will be some force acting on this loop. So for consider the current is counterclockwise, which means that for the left side, the current is going this way, and the B pointing to the right side, so I cross B pointing to upward. So the force acting on the left wire will point to the upward. And as the current is counterclockwise, so this side like this side like this, and this side like this. So consider the right side first. For the right side, the current is going in, and then the B field onto the right side, so I cross B onto the bottom. So you can see for the left side, F pointing to the upward, and this one point to the downward. And consider these two, this side, the current and the B point to the same direction, which means theta equals to which means the angle between the current and the B field is 0. So sine 0 degree is 0. So the force acting on this side is 0, and the same for this one. So we only have two force acting on the left side, and one of them point is for the right side, and they are point to the opposite direction, but they do not cancel each other because they are not acting on the same line. So as long as we fix it here, we have something rotating. So you can consider it will rotate. It will rotate like this. You rotate clockwise. Oh, maybe consider. So this is like this, and then it will. You have some force pushing this up and pushing this down, so it will try to rotate clockwise. So the current going counterclockwise, but this loop will rotate clockwise. If you seeing from this side. Of course, if you watch it from that side, you will consider it is rotating counterclockwise, depending on which side you are looking at it. So now we consider this loop is rotating, so we can define a variable called the torque, 力矩. So the torque equals to NIAB sine theta. N is the number of turn. You consider here is one turn, but maybe you can have more turns. So the number of turns is this N. You may need to be careful in this chapter and next chapter. There are some N, small letter, capital letter, then they have different meanings. So you need to pay attention about it. But here, the capital N means the number of turns in the coil. And A is the area of this coil, the area of it. And then I is the current, B is the magnetic field, very trivial. And then the theta is the angle between the magnetic field and the normal vector to the coil. Normal vector means suppose this coil is a plane, and then the normal vector means the vector perpendicular to this plane. But you can consider suppose it is rotating, so the theta is also varying because so the B field is something like this. If you just seeing the cross section, and then maybe the coil, if you just see from that side, it's just a line, and then this is the normal vector. So we may consider the theta is this one. This one is the theta. So suppose this is rotating, then maybe it rotates to another state. Maybe you rotate like this, normal vector like this. So theta is like this. So suppose this is rotating, the theta is varying from 0 to 2 pi. How do we come up with this? One? So I think we know that F is ILB, and then we need to consider is what is the distance between the force and actually the force is like this, L cross no. Yeah, I cross B like this, and then this is the center point. Maybe we can call it this side is maybe X. So for torque, we need to consider this distance between the force and the central point. So here is so this is theta. So this is theta. So this one should be 1/2 of x sine theta. So we have this one is the R, and torque will be R cross F. And suppose you only consider the magnitude, then it will be RF should be this one cross the F. So it will be something like 1/2 of x sine theta ILB. And actually we have the other part, so we multiply it by 2. So these 2 and these 2 cancel, and x and b is the area. X times L is the area, because x is the length of this side, and L is the length of this side, and this is a rectangle. So x times L is A, So we have I L I A B sine theta. And suppose we have more than one loop, then this force will be n times larger. So we can multiply by n. So we have NIAB sine theta. So next we can consider magnetic dipole moment. Magnetic dipole moment means suppose we can't really have a monopole for the magnetic field. For charge we can have positive charge and negative charge, but here for magnetic field we can only construct the smallest unit is the magnetic dipole. And magnetic dipole can be formed by a coil, a loop, a current loop. So for a current loop, we will have magnetic dipole moment. We denote it as mu, the vector mu, and we will use the right-hand rule to define the direction of the magnetic dipole moment. So suppose this one is counterclockwise, and then you use your right hand to follow the direction of the current, and then your thumb will point to the mu's direction. And for this one, this is clockwise, so you use your right hand, and then your thumb points to the bottom, which is direction of mu. So we consider the direction of mu, but next is the torque. Yeah, suppose this one is put in a uniform B field, then there will be it should be rotating, something like that one. So for this one, you can also consider the magnetic dipole moment. Because this one is rotating. I mean, there's a current going counterclockwise, so the magnetic dipole moment should point to the normal vector direction. So for the normal vector direction, you cross product with the B field, cross product with the B field. So it's something like this, pointing to that side. So that side is the rotational axis. 那个旋转轴是那个torque 的方向。那 torque 的大小就是你的那个力矩乘以那个跟那个力的 cross product。But for magnetic dipole moment, we have mu cross B is the torque. And yeah, for the coil, mu is NIA, which is the current times the area and times the number of coil. For a single coil, then you may consider the magnetic dipole moment is the current times the area of the loop. So which means that the larger the area, then the current moment is then the magnetic dipole moment is larger. Or if the current is larger, the magnetic dipole moment will also be larger. So this is actually an important stuff. So you may consider mu equals NIA, and so here you will have mu, this is mu B sine theta, which is actually mu cross B. So similar to electric dipole, we can define the torque by the magnetic dipole moment across the B field, and then the potential energy will be minus mu dot B. It's a similar calculation as the electric dipole. So yeah, so you can consider the work done will be the delta potential. So we have a sample problem. Okay, a circular coil with 250 turns, an area A of this one, a current of 100 μA. The coil is at rest in a uniform magnetic field of magnitude B equals 0.58 Tesla, with its magnetic dipole moment initially aligned with B. So aligned with B means they have the same direction. In the figure, what is the direction of the coil what is the direction of the current in the coil? So I think this one is very easy. So just now I just mentioned that you use your right hand rule, then you can determine the current of the coil. So actually here we have mu onto the right side. So the coil, if we just draw it like this, then use the right hand rule, you know that the current is going like this. So current going like this. So this is the front, this is the back. I just draw it like this, so that you know that this is the back, because it's hard to draw the 3D stuff in a 2D way. So this is the front. Okay. Okay. So next, how much work done? How much work done would the torque applied by an external agent to have to do on the coil to rotate it 90 degrees from its initial orientation, so that mu is perpendicular to B and the coil is again at rest. So we need to make it like this. And then still at rest, which means that there are no additional kinetic energy. Only change the potential energy. So we can see that the work done on it will be, for the final stage, U 90 degree minus U 0 degree, because at the beginning they are aligned. So 0 degree between them, but finally you want this coil to be perpendicular to it, so finally it will be 90 degree. So we have U theta is minus mu dot B, which means that it should be minus mu B cosine theta, because in the product we use the cosine. This is 90 degree, and then minus mu B cosine 0 degree, which is so this one is 0, this one is 0, this one is 1, So this one disappear. So there are two minus sign here. So then finally we have mu b, and mu is actually NIA b. So we just plug in all the numbers. So n is 250, and then I is 100 mu, 100 times 10 to minus 6. A is 2.52 times 10 to minus 4, and then B is 0.85. So finally, it would be 5.36 mu J. So actually, if you just this is how to say, this is a special case because it will not stay in this situation for a long time or for a long time. Because you can imagine there are some potential energy if you just make it perpendicular to the B field, and if you just release it, then it will somehow like you have the B field, like this, and then this coil is perpendicular. You consider it as a coil rotating this way, rotating this way, rotating this way. But I just make it like this. No, it should be perpendicular. You make it perpendicular is somehow like this, because this is the normal vector. This is the normal vector. So this normal vector, we have a 90 degree, we have 90 degree. So you can consider, if you just release it, it will somehow go this way. And then somehow like this. Somehow like this. It is somehow like if you have a curvature here, then you place a ball here. They will go down, go up to here, and they will go back here, and they go back, and just go back and forth. If you consider there are no loss for this, for the frictional force, but here you do not consider there are any loss here, any energy loss here, so it will somehow like that.